Okay. Today I will present a paper titled A Sober Look at LLMs for Material Discovery. Are they actually good for Bayesian optimization or molecules? And this paper was published at ICML 2024 by Augustinus Christiardi et al. At Vector Institute, and they are from this University of Toronto, Waterloo, and British Columbia. So the main question of this paper is actually quite useful for Bayesian optimization over molecules. So the interesting point of is this that the authors are not simply asking whether LLMs can understand chemistry, and they ask more specific question. uh, do the representation of learned by LLMs actually help us find better molecules through Bayesian optimization? And skip to the background. First, let me briefly explain the problem settings. Material discovery is essentially a search problem, and suppose that we want to find a specific molecule with a particular property, like as if the uh, prop, Segel AI in Segel AI, professor has once told me to about the solar panel material like that. That kind of test can be a problem. So there can be an enormous number of possible candidates, but evaluating each candidate can be very expensive. So ideally, we don't want to evaluate every possible molecules. So we should select only the most promising candidates, and this is where Bayesian optimization becomes useful. The basic idea is that we first evaluate some molecules and then use those observations to build a model of unknown objective function. So based on the model, we select the next molecule to evaluate, then we observe its actual property, then update the model and repeat this process. So here's some example of figure. So this is a sulfuric acid, and the prompt asks to the model what is the molecular mass of this. And here's some spoiler, and the LLM seem to understand chemistry, but they often produce completely wrong answers like this. And actually, these two are all wrong. So this pros the molecular space search is estimated to contain at least 10 unique molecules, and while only a tiny fraction has been experimentally reported. So researchers work with a smaller accessible or synthesizable candidate library and need to identify promising candidate with as few expensive evaluation as possible. So LLMs provide a potential source of pre-trained prior knowledge. If their representations capture chemically meaningful information, they could improve the surrogate model and therefore make agent optimization more sample efficient. But in previous works using LLMs, it has some primarily relied on heuristic prompting or in-context learning rather than principled Bayesian surrogate models. So they obtain uncertainty from token probabilities or variability across generated outputs. However, these estimates originate from point estimated non-Bayesian LLMs and therefore do not directly represent the Bayesian posterior over the optimization functions. And it is also unclear whether the apparent chemistry knowledge of general purpose LLM translates into the representations that are actually useful for chemistry focused Bayesian optimization. The paper therefore investigate these questions directly. So as noted as such, so existing approaches has about the existing approaches. Bayesian optimization has been widely used for molecular discovery, and they include these uh, an LLM-based molecular optimization method such as BioLift use in-context learning with models such as GPT-4 or Llama 2 to select molecules but estimate uncertainty heuristics from LLM outputs. Biochemian studies the use of text embeddings with Gaussian process surrogates for Bayesian optimization of chemical reactions. PEFT methods such as LoRa provide an efficient way to adapt pre-trained LLMs, while Bayesian methods such as Laplace approximation can be applied to the trainable parameters. In this paper, the central idea of this paper is separating molecular representation from Bayesian uncertainty estimation. Pre-trained LLM converts the molecular smiles representation, which is a notation as I showed in this shape. Uh, this representation into a final layer embedding, while Bayesian surrogate predicts the molecular property and models its uncertainty. So they they propose two types of models. Two types of surrogate are considered here. First one freezes the pre-trained LLM and use its embedding directly. And second adapts the LLM using PFT and performs Bayesian inference over the trainable 50 and regression head parameters. So the convert in the experiment, they convert each candidate molecules into a textual prompt representation, primarily its smile stream, and then extract the molecular representation using pre-trained LLM and use it as input to a Bayesian surrogate model. Then compute the posterior projective distribution, select the next molecule using an acquisition function such as Thomson sampling, evaluate its true property, and add the observation to the Bayesian optimization dataset. For adaptive feature models, reinitialize and train LoRa parameters using the observation collected so far, then apply Laplace approximation to obtain the posterior predictive distribution before selecting next candidate. So the key component of the pipeline is about like this. So LLM feature extractor converts the molecular representation into a continuous final layer embedding. Then, and Bayesian surrogate is a function that models the relationship between molecular representation and target properties while providing predictive uncertainty. Gaussian process is a Gaussian process provides a standard Bayesian surrogate for molecular representation. Laplace approximation is approximates the posterior around the map estimate and provide uncertainty for neural network-based surrogate. And LoRa uplift is a pre-trained LLM, and Thompson sampling is a uses sample from posterior to select the next candidate and balance exploration and exploitation. In this training, the surrogate parameters are trained by map estimation and then which combines the log likelihood and observed molecular properties with prior over model parameters. And they trained four fixed feature models. The LLM parameters remain frozen. Yeah. Oh, I already. So they use the data set called many kind of data set that includes various kind of molecules and each kind of specific uh, uses. And in the experiment, they performed the Bayesian optimization over predefined discrete molecular candidate pools. So, which means each candidate has all every candidate has ground truth property obtained from physics-based simulations. So they and the representation include many kind of existing embeddings, and they from some kind of chemistry models such T5 base or T5 gem or some llama models, and the fixed feature model uses Gaussian Gaussian progression or Laplace approximated neural networks as a surrogate. So they use the metric as a best objective value and GAP, which is a normalized and problem independent measure that allows bio performance to be compared and aggregated across different data sets, and hypervolume, which is a volume under current Pareto frontier for multi-objective BO, and monetary and computational cost, which is used for the GPT-4 based and approaches. So they compare these baselines, which is first thing is just a random search, and like then GP plus Morgan fingerprint. Then they use Laplace approximation and these kind of methods, which then also so this is shows the result of summarized result is in this figure, and you can see the highest highest score is by LA Mo from product. So the general purpose LLM features from T5 or GPT-2 and Llama is generally underperformed the simple Morgan fingerprint baselines despite the apparent chemistry knowledge demonstrated by these models. And chemistry specific representations, particularly T5 chem and Wolframer, are substantially better suited to molecular BO than general purpose LLM. T5 chem performs best overall multi-objective experiments in the early stage of optimization. Wolframer can perform better, but it is eventually surpassed by the LLM-based chemistry specific models. Prompting affects BO performance, and T5 can generally perform best when the input is simply smart string, consistent with its pre-training format, while more prompt engineering is not required to obtain the strong performance. GPT-4-based BO Lift performs substantially better than Llama 2 version, but remains less attractive than small chemistry specific LLM combined with a principled Bayesian surrogate. Uh, GPT-4 BO will run cost approximately 12 to $18, reaching $75.8 for five random seeds in the reduced experiment. LoRa-based fine-tuning improves BO performance for both T5 and T5 Chem on most problems. However, T5 Chem fine-tuning decreased performance on the photovoltaic task. So they've done some more qualitative analysis and they, they used only with the Laplacian approximation because they worked generally better than the other things. Uh, so fine-tuning does not always improve performance on the photovoltaic problem. T5 Chem fine-tuning decreases BO performances. The others attribute this degradation partly to using the same LoRa and Laplace hyperparameters across all problems, rather than tuning them on each individual task. Adaptive feature models also require repeated LLM forward pass over the remaining candidate pool at every BO iteration. This is more computationally expensive than fixed feature models whose LLM representation can be cached. So the paper directly tests whether LLMs are actually useful for principled molecular bio instead of assuming that their apparent chemistry knowledge is sufficient. But and it clearly separates representation learning from Bayesian uncertainty estimation, allowing the LLM to provide prior information while the Bayesian surrogate handles uncertainty. This evaluation covers more multiple molecular properties, six single objective problems, and two multi-objective problems, making the central conclusion less dependent on a single benchmark. The comparison with GPT-4 considers not only optimization performance, but also monetary costs, showing the practical advantage of small chemistry-specific models. The Bayesian PFT formulation provides us principled way to combine parameter efficient adaptation with posterior uncertainty estimation. But, but the study focused on discrete Bayesian optimization over predetermined molecular candidates is, and does not evaluate uh, continuous molecular optimization or direct generation of new molecules. The experiments are limited to chemistry, so the conclusion about domain-specific LLMs may not directly generalize other scientific domains. And fine-tuning introduces additional computational cost because LLM features cannot simply be cached throughout the BO processes. The experiments do not fully identify which properties of chemistry-specific representations are responsible for their superior Bayesian optimization performance. And the, um, so, so to conclude, I will summarize the paper with 3 points. First, LMs are not inherently good Bayesian optimizers, so simply using large general purpose LLM does not guarantee useful molecular representation. And second, domain specific knowledge is in in this in this research, chemistry specific models perform much better than general purpose LLMs in most cases. And third, representation and uncertainty should be treated as separate components. An LLM can provide a useful representation, while a Bayesian surrogate can provide uncertainty required for exploration and exploitation. So the overall message of the paper is not that we should stop using LLMs for material discovery. Rather, it is that we should be more careful about what exactly the LLM contributes to the optimization process. And there's some ideas relevant to Segel AI project in this paper. The paper suggests that AI scientists should not assume a general purpose LLM's broad knowledge is sufficient for specialized scientific tasks. Domain specific representation and task specific adaptation can be more important than simply using larger general purpose models. For an AI scientist, that autonomously conducts scientific research, this raises the possibility of using general purpose LLMs for high level reasoning while incorporating domain specific models or representation for specialized scientific tasks such as molecular property prediction and candidate selection. The paper's separation of representation learning from Bayesian uncertainty estimation is also relevant to autonomous scientific discovery rather than asking an LLM to perform entire optimization process heuristically. Different components can be assigned distinct roles. And more broadly, the paper demonstrates the importance of empirically validating whether an LLM's apparent domain knowledge actually translates into useful scientific performance. So, and this is a finish of my this is the end of my presentation for journal meeting. Thank you. 사실 케미컬보다는 베이지언 옵티마이제이션이 메인이라서요. 그냥 케미컬의 경우에는 이런 분자식을 이런 식으로 사용하는 기존 방식이 있어가지고 그거에 맞춰서 한 다음에 이제 실험을 시뮬레이션을 할 때 이제 실제 모든 과정들을 프로세스를 직접 LLM이 테스트하게 하면은 비용이 너무 커지니까 그 과정을 이제 베이시안 옵티마이제이션을 통해서 약간 서로게이트 모델로 근사시켜서 그거를 이제 테스트하게 했다 그런 의미입니다. 그러면 이상으로
이거에 맞춰서 프리트레이닝을 한 거예요? 계속 프리트레이닝 얘기도
아,
나오는데.
제 모델 비교 대상 중에 이미 이런 표기법에 익숙하게 프리트레인된 모델들이 이제 있고 몇 개는 그냥 제너럴 퍼포스 모델도 있고 그렇게 비교를 했다고 합니다. 그래서 예를 들어서 T5캠 같은 경우가 이제 그 케미컬 리프레젠테이션에 이미 프리트레인 되어 있는 모델이고 여기 T5 GPT 미디엄 이런 것들은 이제 일반 제너럴 퍼포스 모델들 그래서 얘네들이 가진 화학적인 그 제너럴 퍼포스한 놀리지를 가지고서 이 시뮬레이션을 할 수 있는가 그거를 비교한 거라고 볼 수 있겠습니다. 네, 이상입니다.